right, welcome folks. So, who can tell me why it is that the burglar hung up his own mugshot up on the wall? Because he's dumb?
Yeah. Wait, hung his own mugshot on what?
On a wall. Why did he put up a picture of his own mugshot up on the wall?
That's a calling card, like how the wet bandits in Home Alone would always like.
He thought he looked good.
True. Perhaps. Or it could be because he was
House arrest, no.
trying to prove that he was framed.
Oh my god. That's funny.
I like that one too. I think that's a good one. So, we just finished up with circular motion, and we are now heading into our very last chapter in this class. And it's going to be a short one. It's on pendulums. More specifically, it's on simple harmonic motion, things that go back and forth. Whether it's a pendulum that's swinging back and forth, or whether it's something on a spring that's oscillating, it's the same kind of deal. And we save this for last because it takes into account everything that we've talked about so far. It's not like we're going to be doing force diagrams with all this. We're not going to be doing all kinds of things with energy that's really in-depth or anything, but it does bring in all of the knowledge that you have learned up to this point, from light and sound all the way through force and energy and projectile motion. And you'll kind of see how this all ties together in the coming days. But as for today, we want to focus on pendulums. And those of you at home, hopefully can see this. This is a pendulum. It's swinging back and forth. And there are a couple things about pendulums that we need to try and take note of today. Obviously, you can see it swings up and back. When we're talking about these pendulums, oftentimes we'll refer to its period. And the period of a pendulum is how long it takes for it to go back and forth one time. So if that's 3 seconds to go back and forth, that is equal to its period. And that's something we have to make sure that we're aware of as we discuss these things. Now, in terms of that pendulum's period, we have to try and figure out what affects that period. And I'm going to give you 3 options, and we'll see how well you do with this. We're going to be doing it in a little experiment, but just kind of in short. So here's a little pendulum. This is just like the one you're going to be working with. How many people believe that the period of this pendulum will change as you change the release height? Maybe from here to here to here.
No.
How many people believe that that will change the period of this pendulum?
I don't think so.
Sounds like everybody's saying no. Okay. What about, say, string length? What if I have it swing back and forth on a really long string like this, and then I do the same thing, but maybe make it like super short? How many people believe that will change the period of the pendulum? We've got 1, maybe 2 yeses for sure. 3, probably.
Yeah.
Okay, so that one's a little bit more strongly. What's that?
I guess the weight and the circumference of the actual thing takes.
Sure, and the weight is the next one. So the other thing is, what if we would actually change this mass and make it heavier? How many people think that would change the period of this pendulum? 1. And that's it. Okay. So you will be doing this yourselves just right now in a second here. I'm just going to show you what I want you to do for each of these. First off, when you're calculating the period, you want to let it swing back and forth more than one time. Because just once, there's a lot of, just human error in that. I would suggest letting it swing back and forth a minimum of 5 times. And then that would, if you wanted to actually get your period, you could just divide that number by 5. But you're just going to be comparing the same number of back and forth, so you really don't have to do that for this. But yeah, take 5 oscillations and use that number. When you're doing the release height, maybe do one that's really low like this. then maybe one that's a little bit higher, and maybe a little bit higher like that. You really don't want to go up here because then you get to the point where you start getting, you know, the string tension being different as it goes back and forth, and you don't want that. You want the tension to be about the same. Okay, so that would be for that one. In terms of the string length, that should be pretty easy. Swing back and forth from this length, then maybe this length, and then maybe this length, and see what that does. You can just eyeball it. You don't need to measure. And then mass. This is the one that's most tricky. So I've got a mass here, and you just want to add this mass to the little golf ball. So the way you do that is you simply take the little slit, and you slide it through the string, put it all the way to the bottom, and then you just wrap the string around, and there you go. And now you can just do the exact same thing. What you can do if you want to be real specific is, you know, because it's wrapped around, the string has gotten a little bit shorter. So you could, you know, make the string a little bit longer to compensate for that if you want to get real specific about it. So that is what is going to be expected of you. There are 5 stations. Grab a whiteboard, find a group, and let me know what your findings are in about 5 or 10 minutes. Go! All right, so as a result from your experiment, did you find that release height changes the period of the pendulum? Not really, no. Did you find that string length changes the period of your pendulum?
Yes.
Absolutely. Did you find that changing the mass changes the period of your pendulum? No.
Yes, we did it right.
So, this is absolutely correct. String length is the only thing that's going to change how long it takes for your pendulum to swing back and forth. So, I'm just going to take this one step further because there actually is an equation that we can use to describe this simple harmonic motion. And it looks a little bit like that. It is also on your formula sheet in the very top of the simple harmonic motion box, with a few other equations that we'll get to later. But in this equation, T represents, of course, its time, and here it represents the period to go back and forth once. L is the string length, and G is your gravitational constant, 9.8, so long as you're on Earth. So, this is actually an equation you can use to figure out what the period of a pendulum is going to be. You'll notice that there is no release angle here. You'll notice there is no mass in this equation, so those two things actually don't make a difference. If you notice there was a difference with release height, you might have just released it from a bit too high or something like that. But it's interesting because, you know, it seems like, you know, this is moving so much slower than this, you'd think they should be different numbers. But, you know, if you're moving faster, you're covering a greater area in this case. And when you're moving slower, you're covering a smaller area, and those two things kind of end up canceling each other out. So yeah, string length is the only thing that's going to affect the period of your pendulum. Now, before I let you get going on the final piece of homework you're going to do for me this year, this is an equation that you can use when you're off at college, whether you take a science class or not, because you'll probably end up in something that's known as a PIT class. If you're going to college, at least that's what they were called when I was there, you'll have these classes that you're pretty much required to take to make you a well-rounded student and all that. And so what that means then is you don't really have a say in whether or not you take them. So you have enormous class sizes because so many people are required to take it. So they were in these giant pits where, like, the teacher's in the very bottom, and you've got 300-400 kids going up, you know, in that whole class, maybe 3 stories or 4 stories tall. So I was in one of these pit classes, just bored to tears. And so while I was doing my best to stay awake, I remembered that I'm a physics person. And a physics person doesn't ever have to really be bored. What I noticed is that hanging from the ceiling above the professor was a little microphone. And that microphone was ever so slowly swinging back and forth due to the breeze inside that room. And I knew, you know, I can actually time how long it takes to go back and forth. I wonder how long that massive microphone string is, the microphone cord. And so what I did is I just used this equation up here. This equation up here to figure that out. Because it doesn't just solve for period. You can also use it to solve for the string length if you have the period. So I'll just do that for you real quick, and then I'll turn you loose. So if I want to solve for length, I want to get this L all by itself, and I can just do a little bit of funny algebra to do that. So first thing I want to do is get rid of the square root. So I'm going to square both sides. So that makes the 2 a 4. And that makes the pi squared. And that's just L over G because it gets rid of the square root sign. So then I'm going to divide both sides by 4 pi squared. And then I'm going to multiply both sides by G. And that then is equal to the string length. So all you got to do is plug in the amount of time it takes for it to go back and forth once, multiply it by 9.8, of course you square this, and then you divide it by the product of 4 pi squared, and out pops your string length. Now that would be in meters, so you'd have to divide by about 3 or 3.1 to get it in, well, multiply it by 3 or 3.1 to get it in feet. But yeah, kind of interesting that you can do that. If you're doing your best to stay awake in a class that you really don't want to be in. So yeah, I don't know if they still have those hanging microphones, but for your sake, I hope so. Okay, any questions on this? Again, this G value is 9.8, but on the worksheet you'll find that you're not going to spend all your time on Earth, and it will point out exactly what that G value is for you then.